Welcome back, everyone. So, last time we sketched out the big picture of Duhon's looping motion. But today we're going deep. We're getting under the hood to see how this thing really works, what its core engine is, how it actually builds our reality from scratch, and maybe most importantly, the bold, testable claims it makes about the universe.
So here's our game plan. First, we're going to look at the special math that keeps DLM from, well, blowing up. Then we'll watch it build an entire cosmos, step by step. After that, we'll see how it squares up against some of physics' most stubborn puzzles. And finally, the ultimate test, the predictions that could prove it right or prove it wrong.
All right, first up, the engine room. You see, any theory of everything lives or dies by its mathematics. And DLM's approach is really unique because it was built from the ground up to avoid the catastrophes, those pesky infinities that literally break other theories right when things get interesting.
And that gets us to the absolute heart of the matter, singularities. You know, these points of infinite density at the Big Bang or inside black holes, they're basically where our current physics just throws its hands up and says, I'm out. They are mathematical dead ends. So, how does DLM get around this roadblock?
Well, the solution is just incredibly clever. You can think of it like a two-calculator system. For all the normal stuff, day-to-day physics, DLM uses the standard math we all know and love. But for the absolute extremes, we're talking the universe's first nanosecond or the core of a black hole, it switches over to a special no-zero calculator. This system literally forbids dividing by absolute zero. It puts a floor on how small things can get, making sure the equations always spit out a sensible answer. Physics never breaks.
And this no-zero rule isn't just some abstract math trick. It points to something physically real. And that brings us to the star of the show, the phi field. Now, in DLM, this isn't just another field among many. It's the only field. It is the fundamental fabric of reality. Everything you see, everything you are, space, time, matter, forces, it's all just a different vibration, a different ripple in this one single oscillating entity. It's like the universe's primordial heartbeat.
Okay, so we have this incredible engine. How do we get from that one fundamental oscillation to, well, all of this? The vast, complex universe we see around us. DLM lays out a really clear step-by-step process.
So forget the chaotic single-point explosion of the Big Bang. This is a much more orderly creation story. It all starts with the phi field's oscillation. Not a point, but a tiny energetic loop. The energy from this vibration naturally kicks off inflation, stretching space-time like crazy. Then, the really cool part, the hydronova. That's when the field's energy basically condenses, like steam turning to water, into all the fundamental particles. And finally, that rapid expansion keeps this new cosmic soup smooth, preventing any new singularities from ever forming.
I absolutely love this quote because it paints such a vivid picture. Don't think of a violent explosion. Instead, imagine a powerful, energetic swelling, like a cosmic pot of water coming to a boil. It's a process that creates everything we see smoothly, and it neatly sidesteps the whole mathematical mess of the Big Bang singularity.
Okay, so with this really elegant origin story and its no singularity math, DLM is now geared up to go after some of the biggest unsolved mysteries in physics. So let's see what it can do. Let's start with the heavy hitters, black holes. According to Einstein's general relativity, deep inside every black hole is a singularity, another one of those points where the laws of physics just give up and all the information that falls in is just gone, forever.
But DLM, with its built-in no-zero rule, says, not so fast. It argues there is no singularity. Instead, the center is a tiny, unbelievably dense, oscillating loop of that same phi field. The physics is extreme, for sure, but it's not impossible. And here's the kicker. This means information isn't actually lost, it's just stored in this really exotic state.
Now let's jump from the infinitely large to the incredibly small, to the quantum realm, and what Einstein called spooky action at a distance. You know the deal. How can two particles, separated by light years, instantly know what the other one is doing? It seems to break the cosmic speed limit.
DLM completely reframes the problem. It says the particles aren't communicating at all. They were never really separate in the first place. Think of them like two leaves on the same tree. If you shake the root, which is the phi field in this analogy, both leaves rustle at the same time. The spooky connection is just a ripple through the one thing that connects everything.
And DLM doesn't stop there. It even takes a shot at one of the $1 million Millennium Prize problems in mathematics. To put it simply, the question is, why do the particles that glue atomic nuclei together, gluons, act like they have mass when the basic theory says they should be massless? It's a deep one.
And this is where it gets really cool, because DLM connects the very small to the very, very large. The solution isn't just hidden in some dense math equation. It's written in the history of the cosmos. As the universe cooled down after the hydronova, the strong force sort of froze into its current state, and that process naturally gave mass to its force carriers. The answer is a direct relic of the universe's birth.
So, okay, DLM has these elegant solutions for old problems. That's great. But a real scientific theory has to do more. It needs to make new, bold, and, this is the most important part, falsifiable predictions. And this is where DLM really puts its money where its mouth is.
And here they are. And look, these aren't vague, hand-wavy ideas. These are hard numbers and specific signals we can actually go out and look for. It predicts a very specific mass ratio for neutrinos, something our next generation of detectors could spot. It predicts faint echoes in gravitational waves, we'll get to that in a sec, a specific rate at which quantum states fall apart on their own, unique patterns in the afterglow of creation, the cosmic micro background, and even a possible candidate for dark matter. Every single one of these is a pass-fail test for the whole theory.
Now, of all of these, the most dramatic, and maybe the one we could test the soonest, has to do with gravitational waves. DLM predicts that after two black holes merge, the new ringing black hole should give off a series of faint echoes at a very specific frequency, right around 250 Hertz. If we found that signal, wow. It would be the smoking gun. It would be revolutionary. Because it would mean that space-time isn't the smooth, continuous sheet we thought it was. It would mean it's actually grainy, built from those tiny oscillating loops of the phi field, the absolute foundation of DLM. And observatories like LIGO are listening for exactly this kind of thing right now. You know, it all brings us back to this fundamental goal in physics, summed up perfectly by Einstein. The whole point of a theory like DLM is to take all the mind-boggling complexity of our universe, from quarks to quasars, and show how it all emerges from one single, simple, oscillating field. And that leaves us with this final, really tantalizing question. If our observatories do detect those 250 Hertz echoes rippling across the cosmos, are we just hearing the dying ring of a black hole? Or are we actually, for the very first time, hearing the fundamental rhythm of the universe itself, that cosmic heartbeat that might have been beating since the very first moment of time? It's a pretty profound thought, and who knows, future discoveries might just give us an answer.